As promised, we're going to use arc length to find something more powerful. So we want to figure out how to find the surface area. Now remember, we were in the disc and washer as well as the shell method, finding the area of a disc or the area of a cylindrical shell, and then you add them all up to come up with the volume, right? So you take a two-dimensional thing, which is area, and you stack them and stack them and stack them to find the volume, right? So what if we take a one-dimensional thing, which is what arc length is? You thought you'd never see my vase again, but you were wrong. All right, so arc length, just imagine here. Arc length is finding the length of this piece of string, right? So this piece of string goes along this vase from end to end. And when you're finding arc length, you're saying, hey, okay, if I take that length of string and I stretch it out on my fancy mysteries of the deep ruler, right? How much length do I have? That's what you're finding when you have arc length, right? It's a linear thing. So it's one dimensional. But what if I stack them up? What if I take my arc of this string and I start thinking about taking that string and I start wrapping it around the object, right? String after string after string, stacking them up as they go around. Well, then what would I have? Then I'd have the surface area, right? So if you think of what we were doing, which was taking these pieces in order to find that arc length and then letting the number of pieces go to infinity. But if you rotate it around the object, then you'll have formed this vase and you'll be able to find the surface area. So to reiterate, to find volume, we stacked up areas. To find surface area, we'll stack up lengths, right? So this seems like, oh, I would never need this app, but this is exactly how they do computer animation, like for Pixar or for motion capture for the Lord of the Rings, Gollum in the Lord of the Rings, or Rocket in Guardians of the Galaxy. Or actually, I think the lead from Avatar is a picture that came up here, right? So they put all these dots on their faces and they have little balls on their suits. And what they'll do is the computer will capture where those balls are. They create lines, create skeletal frames. You can see it right here, right? They'll create skeletal frames. And then when they add motion to it, when they rotate it around, it creates the motion of the character, right? That's how they do it. So they're using the calculus, to be perfectly honest with you, to create characters like Caesar in Planet of the Apes. Fascinating, huh? All right, so now let's talk about what we were doing. So what we want to do is we want to take our arc length and we want to rotate it around. So let me just, so note, to find volume, which is a 3D thing, we added areas. Now we did it either of general slices or, because not everything was perfectly cylindrical, but general slices, discs, washers, or, oops, I'm running out of room, cylinder shells. Right? So we add 2D areas to find the three-dimensional volume. Similarly, to find surface area, which is a two-dimensional thing, right? So that's a 2D, right? So two-dimensional thing. To find surface area, we will stack up, we add arc lengths, which is a one-dimensional thing. Right? All right, so let me grab the next page here. So you imagine taking your arc, like my string on my vase, like this, and then you imagine swinging that arc around. And so it forms a circular path. So if you take a section here of that arc and you imagine swinging it around, it's going to form a circular path, right? because these are only true for rotational objects, which is what we're working with. So we're assuming the object is rotational. Now the distance around that circular path will be the circumference of that circle. Well, it's the circumference, which is 2 pi r. Okay, so now how does that help us? Well, that's going to get us the surface of revolution, because what we're going to do is we're going to take the arc length, which you can see right here, because the arc length is this bit up on the path, right? That arc length. And that is found, well, by most of the stuff, but this part in particular, that's the arc length, right? So you take your arc length and then you multiply it by 2 pi r. R for us is f of x, because your r, let me put that on there in orange. This radius right here from the outer edge of the string back to the center of the vase, that's r. It's the same as right here, which that must be f of x, right? Because that distance right there is from the function back to the x-axis. So that r is f of x. Okay. And that's this right here. So that's r that they're giving you. So it's 2 pi r, right, circumference, times the arc length, and then you add them all up, right? And that's what the integral with the dx does for you. Of course, it'll work the same if you go around the y-axis as if you go around the x-axis. That doesn't really have any bearing on anything. It just means you're rotating in a different direction. Arc length. One last time with my beautiful vase. Come back, vase. Right? So you have your arc, right, which is my string. Oops, if I can get my string to play nice. Come here, string. All right. So you have your arc, right? And then there's a radius, which is from where the string is back to the center axis of rotation down the middle of the vase, right? And then you imagine rotating this string around and it will form the skin, i.e. the glass. And so you'll be finding the area of the glass. So for example, if you wanted to coat this particular vase in gold, it would help if you knew how much area it had, and then you could figure out how much you'd have to coat it with, or if you wanted to paint it. Now, the above formula assume rotation, right? We're assuming this is not for non-rotational objects. The only thing we know how to do with non-rotational objects is to find their volume if they have consistent cross sections with the general slicing method. That's it, you know. So we're assuming rotation of some kind. So assume rotation. This is only, so the formula only works for rotational objects, but that's all we're going to be working with anyway, at least in this class. In Calc 3, you can do other things. So we're assuming rotation around the x or y axis, and we're only going to do the x or y axis, and we're not even going to do those funky ones where you're rotating around like y equals 3 or something like that. It's not going to happen. You could modify them to rotate around any axis, but we're not going to mess with that too much. And now just think about this. We were having problems already, arc length. Like arc length was already an issue for finding by hand, right? So it was already using Desmos a lot to do arc length. This is arc length on steroids. It has arc length with extra bits added in. So we were already using Desmos to find arc length. So we will really use computer approximations for surface area a lot. That's just the way it's going to be. It just occurred to me that I think the function notation I changed on the actual sheet here. I made it g of y instead of h of y, which is not a big deal, but if you want to keep it consistent with the later formula, then you can use g here. Sorry about that. I'll fix that for later. And I just want to be really sure that we're all clear on the differences between all of these things. So arc length, if we imagine my vase, my glass vase from the one time that I was in Italy many years ago. So arc length is the length along, one directional string. sitting on the outside. One directional because I'm not, loop-de-looping around it. I'm going, along the string, right? So I'm going along the vase. One directional string along edge of vase. Let me just pretend it was in centimeters. So that would be centimeters as its unit. Surface area I'm going to fudge it just a little bit, but it's sort of like how much glass. It's not really how much glass. It's more how much paint it would take to cover the outside, right? So how much, but I'll just write it this way. How much glass it takes to make the cup. Let's just do it that way. Keep in mind, this isn't quite perfect, but so this is centimeters squared. And then volume, surface area is a little strange. It's not really how much glass, because glass is also volume, but it's more like how much you could paint on the top of it. So, I mean, I guess how much paint it would cover it. Would cover the vase. That's better. Because it's really technically only the surface. And then volume is how much liquid or air, fluid, there we go, fluid, would fit into the vase. If you imagine the vase is infinitesimally thin, then it would be how much glass makes it up. But no vase is infinitesimally thin, it would break. Okay, so arc length is centimeters, surface area is centimeters squared, volume is centimeters cubed.